Okay, so for part C, we're gonna be writing the balance equation for this right here. It says SiH4 decomposes to form solid silicon and hydrogen gas. Okay, and if you look above, it tells you that SiH4 is a gas. Okay, then you just need to balance it. So right here, and that's it. Easy peasy. Oh, it tells you right here that it's a gas. Yeah, because it specifies. Oh, actually, no, it says it's okay. You don't need the state symbols. Yeah, you're fine. Yeah, this is fine too.
But it doesn't matter if you put it.
Yeah, you're not gonna get it wrong.
Yeah.
But okay, let's go to D. D is super easy. Why does Si have why is the entropy less than H2? Well, this is a gas. This is a solid. And we know by definition that the particles move more in a gas. Or we could say the particles move less. Okay, so that's less randomness. So that's less entropy. That's it. Super easy. That's how I write normally. That's what my journal writing looks like. My wife looks at it and is like,
Particles are fixed.
yeah, are fixed. It's my diary. Dear diary. Today my students made fun of me. Whatever shall I do?
Everything. That's so funny. Needs work for you. I didn't.
And you know what? I respect it. I respect it. You guys fight back. You guys are fighters. You're not victims. I agree. Well, I am hydroxide, so I know they're all so happy and nice. It pisses me off. Yeah. He is. He's a great guy. He's better than me in every single way possible. Anyway, yeah, he's taller than me, better looking, smarter. I don't know. I'm just saying stuff. Okay, let's move on to part E. Part E is also very simple. We just need to use this table right here and the equation that we just wrote. So the equation we wrote was this right here. Okay, and so to find the value of the change in enthalpy, we just need to do products minus reactants. So the delta S of the reaction is going to equal the product, which is wait. Am I tripping balls? I shouldn't have said that in the video. I'm sorry. I am tripping. Okay, so you got SI, which is 18. I'm not tripping. Okay, then we got times 131. And then we just need to subtract 205. Okay, and that should give you positive 75. Yes, that's what I'm doing. We already did D. Yeah, D is because this is a solid. This is a gas. Solids are fixed in place, the particles. I know, today is not a good day. I told Susie earlier that she took her test and I was like keeping it. I apologize. Okay, any questions on part E? So part D, we did this earlier. So solid silicon has less entropy because it's a solid. Solid particles are fixed. There's less randomness, which means the S value is lower. Okay, for part E, we just use this table. We do products, this side right here, minus the reactants. That's it. I don't know. I'm the only sane person on this floor. Are you sane? I am insanity. All right. It is pretty bad. Okay, let's move on to part F. It says that this reaction is thermodynamically favorable in all temperatures. What the? That's a very weird. So it's one at high temperature. Wait, that's phrased very weird. It says it's favorable at all temperatures. Explain why it only occurs at high temperatures. College board, what's going on? Okay, we're gonna ignore this guy. I'm assuming that this is supposed to say at high temperatures. Okay. It is rigged. Explain why the reaction only occurs only at high temperatures. Yeah. Let's ignore that first sentence. College board, what's up, man? What's going on? You're tripping out more than me. Just look at the actual question. Explain why the reaction only occurs at high temperatures. Okay. So if something only happens at high temperatures, basically what that means is that the reactants, they need enough thermal energy to overcome the activation energy. Okay.
Does that make them endothermic?
Yes, in order to overcome the activation barrier, they need to absorb energy, right? And so they need to, yeah.
You say that they're endothermic.
I wouldn't say that because endothermic is referring more to the reaction itself.
Okay.
But you don't know if endothermic means it's at a higher point at the products, and we don't necessarily know that.
So if you said with the G yes, the equation,
No.
it's get that H less point positives, so then when P is bigger, it's bigger, it's more negative.
Yes, that's
So
correct.
eventually becomes negative.
That's correct.
You can explain that.
Yes, that would be perfect as well. Yeah, that's actually probably a better way because you're quantifying it.
Okay.
Something along those lines should be fun. 1.6 kilometers. That good?
Why do you keep saying 1.6?
Because miles. Oh, actually, I'm actually correct. 'Cause you're multiple miles. Yeah, so it should be my fault. My fault. I'll say two. You're 2 miles. You're 2 miles then. 3.2 kilometers. I'm so stupid. Okay, let's move on to part G now. This is still the same FRQ. It's too loud, guys. I can't think, and I'm already tripping today. Okay. Next one, we're looking at the photoelectron spectrum of pure silicon. Do you guys remember seeing this back in the day? Okay, cool. So we want to draw the missing peak that corresponds to the electrons at the 3p sublevel. Now, if you guys look earlier in the problem, we wrote the electron configuration, right? So this peak right here represents 1s2. This right here is 2s2. This right here is 2p6. And we got 3s2. And silicon is 3p what? 3p2. So if you take a look at the peaks, how many electrons are in the 1s2 sublevel? 2. So this probably tells you each of these peaks is 2 electrons, right? And we can also check that with this one right here. 1, 2, 3, 4, 5, 6. So every line is going to be representing an electron. So here, how tall should the peak be? 2. That's it. Something like that. Easy peasy.
Does it matter when it was dry?
As long as it's next to it and very close, because it's the same shell still.
Okay.
Yeah. The energy level is the same. The sub level is different. So they should be right next to each other. And you could tell right here, this kind of gives you your reference. But if it tells you, hey, like, if we were doing something in the next shell, then you would have to probably go down more. Yeah, you have to separate that.
Okay.
Okay, so the next one, I do want you guys to try it out on your own and write out the answer, work with the person next to you. But for part H, you got to talk about the atomic structure. I want you guys to explain why the first ionization energy of germanium is lower than that of silicon. So why does germanium require less energy to remove the first electron than silicons? Take about a minute and a half to do that, and then we'll go over that together. Okay. And you'll want to look at your periodic table for this one. All right, so for this one, we need to look at the periodic table. So we're going to be comparing germanium and silicon. So if we zoom in, germanium and silicon are right here. Okay, now the first thing you guys should notice in the problem is it says that germanium's, sorry, that's the wrong notation. Germanium's first ionization energy is less than the first ionization energy of silicon. Okay, so the first thing you should notice right away is that germanium, it's easier to remove an electron. And the reason why is because the first electron is in a higher energy level, right? It's in a higher shell. So you can just say something like germanium's first energy electron is at n equals 4, or the fourth shell. Or you can even just say it's further from the nucleus, right? Than the silicons. Silicon's first valence electron is at n equals 3, the third shell. And so it's closer to the nucleus. And then you can just say the further an electron is, the lower the ionization energy. Something along those lines. Yeah.
So you're gonna get the number of valence electrons, is the number of shells. Most important.
Yes, that is the most important.
They ever give you one like going to the same shell, that's like the general product.
Yes. And then from that is just electron repulsion, right? The more electrons there are.
Wait, what is further?
Hmm?
What is further from the nucleus?
The valence electrons. So I think if you guys remember, and you guys can think about electronegativity for this. That's also a great way to think about it. You have, as you go to the top and to the right, the electronegativity gets higher. So that first ionization energy also gets higher.
Would they ask a question like doing like sodium or something? Like silicon?
I feel like that, I think that would be a little too easy.
Or like sodium compared to like germanium?
Maybe, but I mean, then sodium is a lot easier to remove it.
Yeah.
Yeah.
Okay.
So yes, I mean, they can theoretically do any combination of them, but just use the principles we talked about. All right, you guys ready to move on to the last part of this FRQ?
Yes.
Okay, let's move on to the last part. So the last part, we're looking at the energy of the photon that's released from this sample. Okay, so you're gonna see wavelength, and so the symbol for wavelength is this right here. Okay, and you're looking for energy, and energy is obviously E. And so you want to look at an equation that has this E energy and wavelength. So we can pull out the equation sheet, and then we got this right here. Okay, and so there are multiple ways that you can do this. Okay, the first way is just use the equation directly. You have Planck's constant right here, so you can plug that in for H. Oh, sorry, there is only one way to do it, sorry. But then we don't have a frequency, so you'll have to use this equation right here. Frequency is equal to the speed of light divided by wavelength, and then you'll plug that in right here. So the energy will be equal to Planck's constant times the speed of light divided by the wavelength, and you just plug those values in. Okay, so the first thing you have to do here is you need to rearrange this equation, the speed of light equation. And then we need to just plug in to this one. And then your final answer, about 4.97 times 10 to the negative 19 joules. Okay, and then Planck's constant is right here. All right. So one rearrangement, and then we plug it in to the equation on top. All right, any questions on that one? Sure. You guys another 30 seconds to copy it down, and then we'll move on. If you guys want to take a look at number 3 and get started, please do that. That one has some lab procedure stuff. You're not writing procedures, but it's kind of like a lab thing. Yeah, take a look at A and B on there, and then we'll go over in a second. All right, so we got all this information. I'm not going to go through it. You guys should have read it as we were going through it, or as you guys tried this out. But you want to write the net ionic equation for the precipitation reaction. Now, if you take a look at the problem, there are 2 compounds that you are combining, right? You got barium nitrate and copper 2 sulfate. Okay, so your equation, so I'm going to write the full equation first, and then we're going to get the net ionic from there. Okay, so we have barium nitrate, and anything that reacts with nitrate is going to ionize. Okay, remember nitrate is Taylor Swift. It breaks up with everybody. Okay, and so it's gonna become this. So that's barium nitrate. And obviously these are all aqueous. I'm just not writing it. Okay, and then we got copper 2 sulfate. Now, since these two are reacting, right, we're operating under the assumption that it's gonna break apart. Okay, because if it doesn't break apart, it's not going to react. So we're going to do copper 2 sulfate. This would be Cu2 plus and SO4 2 minus. Okay. All right. Now we're doing a double replacement because it's precipitation, right? So we're going to be combining the barium with the sulfate. So first of all, actually, before we do that, we don't know which one's gonna. We have to figure out which one is going to become the precipitate. We know that one thing turns into a solid, right? So we need to figure out, is it going to be barium sulfate or copper 2 nitrate? Now, like I said, and nitrate is Taylor Swift. It can't stay with anybody. And so these two are going to stay ionized, which means the precipitate has to be barium sulfate. So your ionic equation will be Ba2 plus aqueous with sulfate, and then your precipitate is going to be this right here. Okay, so the key here, and those are the two precipitation rules you need to memorize. The first one is that alkali metals, the first column, they all break up, and nitrate also always breaks up. And so that's kind of the principle that helps you solve the whole problem. You know that barium nitrate has to break up, and nitrate can't get with copper. And so this is the only thing that can form a precipitate. Okay. So this right here is the answer to part A. All right. Any questions about that? All right. So I'm going to delete it for a second and I'm going to write it back up. So give me a sec. Don't freak out. So the answer here will be a barium ion, sulfate ion is going to form this precipitate right here. Okay, let's move on to part B, guys. So for part B, we're finding the moles of the precipitate. And for this one, we need to refer to the data table right here. Now, it tells you that you're using this amount, this volume of the compound. Well, we don't really care about that. We're basically just trying to find out the mass of the precipitate. Now, it tells you that you collected it in filter paper. So if you want to find the mass of just a precipitate, what do you have to do? Yeah, minus, subtract. So the first thing you want to do is you want to do 1.136 minus 0.764, because if you get rid of the filter paper, you have just the precipitate. Okay, and that's going to give you 0.372 grams of precipitate. Yeah, and then here, you know that the precipitate is barium sulfate. So you just need to multiply that by the molar mass. And I'll give you guys the molar mass. It's going to be, sorry, not divide. You're going to divide by the molar mass. Sorry, it's going to be 233.4 grams in 1 mole. And that's going to give you 0.0016 moles. So 2 steps for this one. First, you need to subtract the filter paper to find the mass of the precipitate. That gives you 0.372. We know that the precipitate is barium sulfate. So we just need to divide it by the molar mass, which is 233.4. And then that'll give us this for our moles. Okay. All right, so I'll leave that up there and then we'll take a quick 5-minute break. And then we'll come back and we'll finish number 3. And then I'll explain what we're doing the next time we meet. It'll be a little bit different. And then, yeah. So we're taking the number that we got from part B. We're going to use this and work backwards using mole ratios in order to find how many moles of copper sulfate we have. So if you guys take a look at barium sulfate, copper sulfate has the same sulfate ion, right? How many sulfate ions are inside of barium sulfate? 1. So it's 1 mole of barium sulfate contains 1 mole of sulfate. Okay, how many moles of sulfate are in copper sulfate? 1. So you can skip this fraction in the middle if you want, but 1 sulfate ion in 1 mole of copper to sulfate. Okay. And so that will end up giving you your moles of copper sulfate, which is 0.0016. Yeah, it's the same thing because a 1-to-1 ratio for everything. Okay. Yeah, so if you want to skip that step, you can skip that step. But if this helps you kind of understand why, that's exactly, you guys are significantly dumber on test days. Because on normal days, you guys are smarter than me. And then you guys take the test and it's like, dude, I look like a genius.
You're the teacher.
What's up? I agree. Yep. So, yeah, just get inside your head. Yes. Yeah. Last step. 0.016 moles of copper to sulfate, and we're going to divide it by the volume. If you look at the information above, it tells you that it's 0.05 liters, 50 milliliters. Solve it. 0.0 about 32. Okay, so that's how you find the molarity of a solution by using how much precipitate was formed.
Why don't we do it with you? Like, totally, like, I'm there, like, this is fine, but then I'll read it a lot harder. I'm like, but yeah, and I read it, and I'm like, that.
I totally understand. That was how I felt too.
Yes, you got 5.
Look at me in life. Dude, you guys are gonna do so much better than me in life. Yeah, you are. School doesn't matter that much.
Yes.
It's not. I am doing pretty good in life. But I think and expect you guys to do a lot better than me. I don't know. Just better. You guys are already smarter than me, so I think you guys already have a leg up. Yes, I think so. Okay. Let's move on to part D. Part D is you want to calculate the volume of copper to sulfate solution that you need to make 50 mils of a weaker copper to sulfate solution. So if you guys take a look at this, what type of problem is this? Yeah, molarity volume, but specifically it's dilution. Because you're taking a stronger solution and you're turning it into a weaker one. Okay, it tells you you want to make 50 mils of the weaker one. So this is very easy. M1V1 is M2V2. If you guys notice on all the tests we've been looking at, this comes up a lot, right? So it might be helpful. Yeah, hopefully it's on your test so you guys can just knock it out of the park. And this is going to tell you how much of the 0.1 solution you need in order to make 50 mils of the 0.05 solution. Okay. And then for this one, you don't need to convert it into liters because you'll get the answer directly in milliliters. Yes, that is great news. Okay. And that's going to give you 25 mils. So you need 25 mils of your 0.1 molar solution to make 50 mils of your 0.05 molar solution. Okay, that's pretty much what this is telling us. Oh, and this is perfect. It goes straight into a procedures problem. So if you take a look at part E, it's asking us, briefly describe the procedure the student needs to follow to make this solution right here using this original solution. Okay, so we already did most of the work. It tells us that we need 25 mils of the 0.1 molar solution. Okay, so all we got to do is explain that process. So I'm going to type it out just so I can write a little less. Okay. But basically, the first thing that you would want to do, okay, is obviously you want to measure out 25 mils of your 0.1 molarity solution. Okay, and then it tells us equipment, so in a graduated cylinder. Something like that. So it's just the calculation that we did. Okay. Yes, exactly. And then you just want to say something like add the 0.1 molarity solution to a how much are we making? 50 mil volumetric flask. And then you can just write fill to these line with distilled water. That's it. Yeah, you want to say distilled water. What's up?
Like add some and swirl it.
That's if you have a solid. Yeah.
Okay.
This one's already a solution, so you don't need a swirl or anything because it's already a liquid.
Okay.
Okay. So these are a lot better just because it's already dissolved for you. So we want to use distilled water because if you get like tap water or something, there's actually ions in your tap water. And so if there's other ions present, it could, you know, react with whatever you're working with.
What actually is this?
It's water without ions dissolved in it. Yeah, so boiling is a good way to do it because it turns into gas and then they just condense it. So that's probably the most easy way to do it. Yeah, there's other chemical processes, but that's the easiest. Yeah. So you can make distilled water at home too.
That's crazy.
But your gas bill will go up like crazy because you gotta boil all that. You're gonna hold your lighter. Dude, you'll be there for days. Okay, guys, you guys ready to move on? Alrighty, let's move on to part F. F is a chart, and I do want to give you guys some practice reading charts. So I'll give you guys about 2 minutes to try this one. Okay, so take 2 minutes to try out this part F. If you finish early and you want to go to part G, you can. But then we'll go over just part F in 2 minutes. Okay, guys. So for F, what you want to do is you want to just look at the absorbance. So it tells us the absorbance of the solution is 0.219. So you want to look around 0.219. Okay, so this is 0.3, 0.2, so a fifth of the way up about. So somewhere around there. And then we go down from there. And that's going to give us the concentration. So this is going to be 0.03. And it looks like it's a little less than half, right? So you can say like 0.03332. The exact range that they give is anywhere. It doesn't even give you a range. As long as you're around 0.035, you're good. So about half. So I'm going to assume anything from 0.03 to 0.035. That should be fine. Yeah, that's a. It does definitely look like it's less than half. Yeah, you might be pushing it, but I think 3.6 should be fine. Yeah, 3.6 should be fine. As long as you're not like 3.9, 3.8, like way far to the right. It just says, yeah, it just says estimated value, but it doesn't give you a specified range. Okay, everybody good? All right, last one, and then we will, yeah, we'll be done for today. Okay, so this is another experiment one, and this is actually very similar to the problem that we did last time. So I'll give you guys 2 minutes to try this as well. But yeah, take a look at the question, and then see if you guys can remember. You can look back at your old notes if you'd like. See if you guys can figure out if the concentration will be greater, less, or equal. Okay, so if there's water in the cuvette, is that going to increase, decrease, or same concentration? Yeah, you're going to have less concentration. The concentration will be less. Okay, and obviously, because the water will dilute your solution, will the absorbance go up or down? Down, yeah. So both the concentration and the absorbance will go down. Okay, and it's because the water in the cuvette will dilute your solution. Okay. Because there's less particles inside the cuvette to absorb the light. Yeah, you need stuff in there to absorb it. Okay, so before we close up, let me just briefly explain a couple things. Like I said earlier, after today, we got 3 class sessions together for the AP test. So to help you guys out a little bit, if you guys go on Canvas, I put up all of the old AP FRQs and the answer keys from starting from 2010. So that's even before I took the AP Chem test. Okay, so it was like going down memory lane when I saw my old one. Okay, yeah. Yeah, I was like, this easy. No, but it's yeah, so it's there for you guys to practice. A good way for you guys to see what kind of topics are stressed on the AP test. And if you guys want to take a look at it with the answers, that'll be very helpful. It'll kind of show you how it's scored. Next time we come to class, I'm not going to be lecturing the whole time like this. Instead, I'm going to break you guys into pairs or threes, and you guys are going to have some time to work on the AP test together. So for your long FRQs, you should expect to take about 20 minutes to do them and about 10 minutes to do the short ones. So that's really fast. So next time we come, you guys will work with somebody. I'll print out an FRQ for you guys, and I'll give you guys either 10 for a short one, 20 for a long one to work on it together. We'll briefly go over it, and then, you know, we'll just keep going until the AP test like that. Okay? Yes. No.